Good morning all. I hope you all had a good weekend and back, ready, raring to go. We should have, sorry, just looking at this, let's get rid of that, brilliant. So you should have work set on Seneca by your teachers this week. We're going to start doing Chemistry 1. So we're going to be looking at atomic structure. We're going to be having a look at the periodic table. We're going to be looking at some of the history behind it. So there's a bit of overlap there with Physics 4. So we'll have that as well. And as usual, any questions, just ask. So let's make a start. Brilliant. So atom by definition is Latin. Morning, Tanishka. Atom by definition is Latin for uncuttable. So if you go back sort of far enough, back to sort of some of the Greek philosophers, this was before we actually started doing science and actually testing theories. This was where lots of people would have been stood around, they'd have been discussing ideas. They would have been doing science because they would have been using their observations, but possibly not actively testing those observations afterwards. So they came back with this idea that if we were to cut something up and we were to keep cutting it, actually what we would end up with is a particle that we couldn't cut up anymore. So in other words, we couldn't get any smaller. And they came up with this word uncuttable. So the Latin for uncuttable is atom. And that's what we still call as atoms now. Now, we know that's not quite true because we know that atoms are still made of other things. So actually, it's not a problem. We can still cut atoms apart, but that's where the term came from. Now, atoms are really, really important because they make up everything around us. Now, we only know there's about 120, 130 different atoms. We're still sort of creating new ones. Let me just turn that down a bit. We're still creating new ones. But realistically, that's the sort of number we're looking at the moment. Yet, when we look around us at the moment, there are hundreds of thousands of different chemicals. So what we're actually looking at then is this idea that atoms are these building blocks. So atoms are a bit like Lego. Absolutely love Lego. Kids like playing with Lego. We want to make something new. What we're going to do is we're going to start building those blocks together. We're going to start piecing them together. But we want to make something new. We're going to pull them all apart and we're going to rearrange them into a different structure. And that's pretty much exactly what happens when we're looking at chemical reactions. We have our atoms. We've got our base building blocks. And depending on the number of them that are joined together and depending on not just the number, but how they're joined together and the different types, depends on the product we end up with. Okay, so we've got this idea there. There are a few sort of definitions that we need to make sure that we get down. Some people get a bit confused with these ones. We've got atoms. I'm going to put compounds down. I'm going to put mixtures. And I'm going to put molecules down. So we've already sort of talked about atoms. Compounds and molecules are similar, but there is also a major difference. A compound is a molecule. Okay, but a molecule... so we've got that side of things, but there is something very specific about compounds. The term molecule just means we have more than one atom that is chemically bonded together. So in other words, it has made a different product. And as we're working our way through, we're going to be using words like products and reactants quite a bit. So we can put those down as keywords as well. So if we join molecules together during a chemical reaction, the product is going to be different. Those atoms are chemically bonded together. We therefore have a molecule. Now, the compound is very, very specific because it is only a compound if there are two or more types of atom in that molecule. So, for instance, if I had something like hydrogen, or we could have oxygen, and we're going to do lots more on chemical bonding in chemistry 2, so I'm not going to really focus about that now. We could have some sort of bigger molecules there. I mean, some of the sort of big diamond structures, we end up with sort of lots of sort of bonds between these. These are all molecules, but they're not compounds. Okay, morning, Olivia. So that's quite a big distinction to make. If, however, we have something like water, or we had carbon dioxide, or we could have maybe silicon dioxide. So we end up with structures looking a little bit like diamond, but sort of discrepancies there. So these ones here are our molecules. In fact, they're all molecules, but those ones are not compounds. These ones would be compounds, okay? So, let's just get that a little bit better. Okay, those ones are going to be our compounds. Morning, Chris, good to see you. So make sure you've got that difference. When we're looking at mixtures, mixtures would be where we have different molecules, or it could just be atoms, it could be compounds, when they are not chemically bonded. So the air around you is full of nitrogen, it's full of oxygen, it's full of carbon dioxide. But those are not joined together because they're actually floating around, and they're not making new stuff, they're not making new products. So that would just be a mixture. And generally mixtures are fairly easy to separate. Whereas with a compound, we need to do another chemical reaction in order to separate them out. Now, with mixtures, we can separate them out quite easily in class. So I'm just going to talk briefly, because again, we'll talk about this as we go through later on. Some of the different ways of separating mixtures out, just to make sure we're happy with these. So when we're looking at this, we're looking at, I'm going to put another couple of keywords down here. Soluble, solvent, solution, okay, and solute. So probably one of the easiest ways of separating out a mixture, so one of the ones we do in school, is when we're looking at filtration. So filtration, we know we have our filter funnel, and we will generally put it over a conical flask. Really should have used the line tool on that. Very badly drawn. But what we're trying to look at removing is this insoluble. In other words, any solid that does not dissolve into your solvent, we're looking at removing from the rest of the liquid or the solution. So this might just be water, but it could be a solution as well. So for instance, if we had a mixture of, the ones we do in school is generally really boring. We're looking at sand and salt, just because it's a really simple one for students to do. In fact, some schools do this when they're at Key Stage 2. What we're actually looking at doing is we've got sand, which is insoluble, and we add water to basically the sand and salt mixture. The salt will dissolve into the water, forming our solution, and the salt in this case is the solute. Solute is just the solid that's dissolving, and then we can separate them out. So it's a way of separating an insoluble solid from a solution or liquid of some sort. Apologies if this is quite basic, but it's just making sure we've got some of these definitions down. We'll get onto the more tricky stuff in a moment. We then have ways of separating liquids. So we're looking at separating mixtures of liquids. The easiest one that we do in school is chromatography. So chromatography, we know, and this comes up much later on as well, so I'm not going to spend ages on this. We do thin layer chromatography in school. So we will have a piece of, we usually do filter paper. I know some of you guys we've used the actual silica coated plastic, and they work really, really well as well. And what we'll have on here is we'll have a line drawn in pencil. We'll have some dots on there. And as the water moves up, it's going to separate those out. So it's a way of separating a mixture of liquids. Those of you that go on and do chemistry or applied sciences in more detail later on, you'll look at column chromatography. So rather than just a qualitative, which is what this is like a qualitative analysis. We can actually do column chromatography, where we can actually collect the liquids afterwards. And even more so at university, it's quite a popular method there. So school, we do thin layer, we do it on paper, but it is possible to separate the liquids as well. Now, if we have a mixture of liquids with different boiling points, we can use distillation. and I will just drop in a picture just as a refresher for you. There's our basic distillation setup. We're heating some water. In this case, we're actually not using a mixture of liquids. We're actually trying to separate out and collect the water from the, well, we've got a soluble solute in the solution. So that would work absolutely fine as well. But we could also use it for separating out mixtures of different liquids with different boiling points. If we want to collect multiple liquids, we would call it fractional distillation. But there'll be a whole topic on that later on. And all we do is we heat it up to the boiling point of one of the liquids. That liquid evaporates. As it evaporates, the vapour moves up, comes into our Liebig condenser, and there is cold water around the outside where it condenses so we can collect them. So just a couple of different ways of separating out some mixtures that's worth you being aware of. Now, when we start looking at atomic structure, we couldn't actually do any of this without the periodic table. So we're going to be using the periodic table loads. Now, okay, I'm a chemist. I like the periodic table. But from your point of view, the more that you can actually learn to use a periodic table, the more you actually get your head round, not so much the intricacies, but you learn where things are on there and what you can learn from it. It's like going into the exam with the answers. It's almost like having a bit of a cheat sheet. One of the reasons I like chemistry is the fact that actually the more you understand, the less you actually have to know, because you can work it out as you go along. So you don't have to have vast amounts of knowledge stored in your head. You just have to be good at applying the stuff that you do actually know. And this is where the periodic table comes in and is so useful. So let's just drop in a periodic table, and I'm going to be coming back to this throughout this session and probably the next one. So this is the periodic table, when it appears, there we go, the AQA publish. This is on their specification. This is the one you want to get familiar with. So this is the information that you will have in front of you with your exam papers. So you don't have to remember any of this. All you have to be able to do is take this information and learn what we can do with it. So what it is worth doing, and I will drop this periodic table into the notes on Google Classroom afterwards. It's worth having a copy annotated so you can start getting your head around what we can do with it. And I'm going to come back to this throughout this topic and throughout chemistry too. So, a couple of key features. We've got the groups going down. So all of these columns are groups. So we don't include the transition elements at GCSE in the groups. I will come back and talk a little bit more about these later on. We don't cover lots of information on these. We do cover some of the properties. We do use the numbers with them, but it's not included in the normal groups as we call them at the moment. Okay, so these are the transition elements. We've got group 1, group 2, 3, 4, 5, and so on. Group 1 we call the alkali metals. Those of you that are interested, you don't necessarily need to know this for GCSE. Group 2 we call the alkali earth metals. Group 7, I'm not going to go through all of them. Group 7 we call the halogens. And group 8 we call the noble gases. Now each group going down, morning Sam, each group going down has elements with similar chemical properties. And I'm going to come back to those towards the end of when we're looking at this. But it's just worth being aware. The reason they're grouped in this way is they have similar chemical properties, so they deserve to be in the same column, which actually helps us out as scientists as well. When we're going across then, we have up here periods. So each row is a separate period. So we have 1, 2, 3, 4, 5, 6, and 7. And I'm going to come back a little bit later on and talk about why those are useful. The exam board give us this key, so we should know that actually the number at the top of the symbol is the atomic mass. The number at the bottom is the atomic number, and I'll talk about what those mean in a moment. But they actually tell you that, which is great, because actually you don't have to remember those words as long as you know what they mean. So the periodic table has every element having its own unique symbol. One of the most common areas that students get things wrong, and as a scientist it just makes me cringe, I want to go and rock in the corner for a few minutes, they get the capitals and the lowercase wrong. Now, this is really important because it's exactly the same in English. If when we're writing a sentence, we'll have a capital letter at the start and we'll have a full stop at the end. Every element has to start with a capital letter. If there are two letters in the name, so for instance, if you notice vanadium here only has one letter, whereas a lot of the others have two, the second letter always has to be lowercase. And you'll get marked down if you don't do that. It can also cause some issues because, for instance, if we've got nickel, nickel's got Ni. Now, nitrogen is N and iodine is I. So we've got the same letters, but those are three separate elements. So if we get the capitals and the lowercase wrong, there is actually some confusion over the molecule that we might be writing down. So it's a really subtle, really very little thing, but in chemistry, this is huge. In all of the sciences, this is huge. So we've got to make sure that actually we get that right from day one. Okay. In terms of where the symbols come from, a lot of it depends on when and where it was discovered. So if we're looking at iron, iron is Fe. So it's ferrous. We're looking at ferrous elements, or ferrous, not ferrous elements, a ferrous element. So that's where the Fe comes from. Sodium was discovered in Germany, so we've got natrium for that one. Pb, brilliant, is for lead. So if you were a plumber, then traditionally, years ago, before we realised that we had toxic chemicals being leaked, plumbers would have worked with lead. If you're a building constructor, working on construction sites, you might use a plumb line, which is a piece of lead or a weight on the end of a piece of string, so that we can work out the vertical wall. And that's because Pb is lead and it stands for plumbum. So plumbum is Latin for lead, which is where the Pb comes from. So some of the letters on these are absolutely brilliant. A lot of them, they link to the name. Carbon, nitrogen, oxygen, fluorine. As we start working our way through, we can see where they come from. But some of the other ones on them, a little bit more obscure. But you don't have to remember any of these. You'll be given it. It's worth being familiar so that you can try and isolate where they are a little bit quicker on the table, so you're not scanning every single line to find it. But the main thing is that we can know what information can we get from this periodic table. Okay? Now, the structure of the atom has changed quite a lot over the years. Let's just go over this side for a minute. I'm going to talk briefly about this again when we do Physics 4. So we're looking at radiation. This comes up again. So this is brilliant because actually there's a massive overlap here. This particular section of the specification is the same whether it's in Chemistry 1 or whether it's in Physics 4. But you do need to be aware of the history of the atom and how it's changed. Now, this is quite a good example of how our ideas, how the theories, how the models that we use change with scientific development. So as we're sort of working our way through, we started off already saying that when we're looking at some of the Greek philosophers, just let me know if the sound's going a bit crazy because the audio bar on here keeps maxing out and I'm not talking that loud at the moment. So if there's a problem with the sound, can you guys just let me know? So when we look at the history of the atom, we said that actually originally the term atom came from this idea of uncuttable. There was another scientist afterwards called Dalton, and again he sort of predicted, did practicals, and he said, yeah, we've got these round particles called atoms. Now, after Dalton, their experiments were done, and they realised that actually there were, thanks Sam for letting me know, there were positive and there were negative charges in these atoms. Now, we didn't know anything about the current nuclear model. We didn't know anything about the current theories. So a scientist called J.J. Thomson, thanks Tanisha, came up with a plum pudding model. So the plum pudding model basically was a round atom. Okay, we've got a round atom, and this was full of positive charge, and inside that there are these negative charges, a bit like plums in a pudding. Not that I've ever really spoken to anyone who's had a plum pudding, but you get the idea. So these were sort of negative charges in an area of positive charge. And they said the pudding type structure, that was the positive charge. And then we had these sort of negative electrons around the outside of that. Now, after that, the Rutherford, this was a lot more recent. Rutherford, oh, hang on, come on. There we go. And Rutherford was assisted by two other scientists called Marsden and Geiger. Geiger students have sometimes heard of because of the Geiger-Müller tube. We're looking at radiation, which he worked on. So let's just bring in another picture here. And I think this is one I've actually used before. There we go. Now, what they did is they shone alpha radiation, and alpha radiation is quite a big, positively charged. It's the nucleus of a helium atom, so it's not just one particle. We're looking at 2 protons, 2 neutrons, but we'll get to those in a moment. So basically, alpha radiation was a sort of big, positively charged particle. Yeah, there is, Sam. It's oh, I don't know if it's on this table. I'll just dive back quickly. No, Rutherfordium is an element, but if you notice down here, there are the lanthanides and the actinides, which normally would fit in where this dark line is here. There is 2 further rows underneath. So yeah, Rutherford did have an element named after him, as well as a few others, but they're in those sort of radioactive ones underneath. But what I'll do in a minute, I'll grab another periodic table and drop on there just so you can see where they are. So they shone these big alpha particles at some very, very thin gold leaf. Now, gold itself is a huge atom. What they actually found out, though, bizarrely enough, was that most of these alpha radiations they were shining through went straight through. If you look at the sort of quantities here, the vast majority ended up going straight through the gold leaf. Now, what this must have meant was that most of the atom is empty space. And if you look at the plum pudding model here, there's no way that could be true, because the plum pudding model is this sort of solid positive area with these negative particles dotted around throughout. But what they were predicting here is actually most of it's empty space, and you wouldn't have got that. So straight away, this plum pudding model was proved wrong, and they were going to have to try and change some of their theories. What they then came up with is that some of this radiation was deflected. Now, they knew the alpha radiation was positive, so the only reason they could come up with that it would be deflected as it was going through was that the nucleus must also be positively charged, because like charges repel. So we've got most of its empty space. We've got this idea that the like charges repel, so we've now proven that the nucleus must be positive. The other thing they came up with is a small number of the particles, and if you look at the sort of quantities, very small, were completely reflected back. So the only reason they came to this was that most of the mass was in a very small nucleus. And it must have been a dense area, because it wasn't actually destroying the gold particles, it was actually deflecting off this alpha radiation. So therefore, most of the mass was concentrated in this very small nucleus. And if you look at the size of an atom, what we're actually looking at with these ones, just bring that back up again, atoms are somewhere in the region of about sort of 0.1, hang on, bring my pen back, there we go. Atoms are about 0.1 nanometers. The nucleus is about 1/10,000th of a size of the atom. And everything else is going to be pretty much empty space. You're going to have the electron shells, but most of the rest of it's going to be empty space. So, and that's quite bizarre actually, because when you start trying to think about the chair that you're currently sat on, or the bed you're lying on, depending on how you're accessing this, the desk, everything around you is mostly empty space. Yeah, it feels completely solid. And that's sort of a bit of a difficult concept to get your head around. But this was all proven by Marsden, by Geiger, when they were doing their experiments. Now, we didn't know anything else at this stage. Have I got a better diagram? Or did I download one? Let me just look. No, but I can bring this one in. So, let's just put that there. Hopefully I haven't covered anything up. There we go. So what we've got here, I've just covered that. Bear with me. Let me just put that up a bit further up. Put it there. This is a diagram, again, taken from the exam board. It's one that you're meant to sort of put into an order, which is why it's not in the correct order at the moment. But we've got the idea. This would have been Dalton. We've got the plum pudding model here. If you notice C is our nuclear model. And this was the model that Rutherford proposed. Notice there aren't any particular energy levels for the electrons. They're just all orbiting. They're whizzing around the outside of this nucleus. And notice there's no neutrons. All we have is a positive charge. So Rutherford proposed the nuclear model. And that is our nuclear model. So positive nucleus, very small, very dense, mostly empty space, electrons in orbit. After that, we had Niels Bohr. And Bohr did experiments and worked out that actually the electrons themselves were in very, very specific energy levels. And you can call these energy levels, we can call them shells, we can call them orbits. You'll hear me sort of move between these and flip between these, and that's absolutely fine. That was Bohr's idea or theory. Again, based on experimentation, this wasn't just him doing philosophy, turning around and going, oh, I wonder if. This was based on scientific observation. And then we had James Chadwick. So James Chadwick came up with, basically, discovered neutrons. Or proposed neutrons. And this was down to the fact that actually, when you looked at, we knew that protons had a mass number of 1. But if you start looking at some elements, the mass number, or most elements, the mass number is much, much higher than the total positive charge. So if the mass number is higher, there must be other particles that are contributing towards that mass number. And in this case, actually, the only way they could predict it is there must be other particles that have no charge. And in this case, it was the neutrons. Cool. So let's bring the periodic table back up here. And let's actually have a look at the atomic structure. Now, this is one of those areas that you need to be able to do comfortably and easily without much thought. In the exam, it's one of those absolute fundamentals, whether you're on a foundation paper, whether you're on a higher paper, whether you're doing triple, it makes no difference. You need to be able to work out the number of protons, the number of neutrons, the number of electrons in an atom, and you need to be able to draw that or write them down. You need to know where they're found. So we're going to put this down now, but it's one of those absolutely fundamentals that realistically we can't move on to bonding or anything else until we've got this written down properly. So let's just take lithium. Lithium, we know, is that. Now, depending on the periodic table you look at, depending on which way round these numbers are. I've given you the periodic table that you'll get in the exams, but don't be surprised if you're looking on the internet if you find the mass number at the bottom and the atomic number at the top. It's not a problem. It's not necessarily wrong. There's no actual sort of definition for this, but the one I've given you here, this is the way it's going to be for you. Whichever one you look at though, the big number is always going to be this mass number over here, okay? So the mass number tells us the number of particles in the nucleus. So if I was drawing lithium, and actually we can only really get away with drawing the first few because actually they get too big for us to work out what's going on. But if I was drawing lithium, I would be drawing 7 particles in the nucleus. There's my 7 particles in the nucleus. Now, I know that these particles, their nucleus is made of protons and neutrons. So the 7 is the number of particles in the neutrons, and it's the number of protons and the number of neutrons added together. The atomic number tells us the number of protons. Now, the number of protons dictates the properties of the element. So if we change the number of protons, we actually change to a completely different element. In physics, we can change the number of protons when we're looking at nuclear reactions. In chemistry, we never ever change the number of protons. The only thing we'll change, and this is sort of later on in the next sort of lesson or two, we may change the number of electrons, but we do not change anything in the nucleus because it changes the chemical properties completely. So the number of protons, that atomic number, tells us what the element is. Any atom that has 3 protons is always going to be lithium, regardless of what else is going on. So I know that 3 of these are going to be protons. That leaves me with 4 particles left, which is the number of neutrons. So for this element, I'm going to have 3 protons. And what you'll probably find as I'm going through this is I end up getting a little bit lazy and I'll put P plus down for protons. I'm going to have 4 neutrons. And in an atom, the number of electrons will equal the number of protons. So I'm going to have 3 electrons. And I've put the shorthand that I'm going to be using for the rest of the lesson here. We just move that out of the way a little bit. So a definition for you here. When we're looking at an atom, we have same number of protons and neutrons. And we can also say it's got 0 charge. And that'll become a bit more obvious when we look through in later lessons when we start looking at what ions are. There is another definition we need to make sure we've got down. And I think it's one because we don't look at very often. Students often forget this particular one. But an isotope is any atom with the same number of protons but a different number of neutrons. Okay, so we need to make sure we're happy with both of those, but atom, same number of protons, has to have the same number of protons because otherwise it'd be a different element, but a different number of neutrons. And there are a few examples of this that we're going to have a look at in a moment. For the moment though, let's just come back to here. One of the sort of summary tables that you really need to make sure that you have and you're happy with, again, it's quite a fundamental, it's a foundation level work, is we need to just make sure we've got the properties of these subatomic particles written down. So I'm going to have my protons, neutrons and electrons. You need to be aware of the mass, the charge and the location. And I should be able to turn that into a line. just so it looks a little bit more like a table. Oh, nearly. Sorry. There we go. So, mass numbers for these two are both 1. Electrons, I would just put down in an exam, at GCSE anyway, very small. It's something like 1 over 2,500, it's very tiny, but you cannot put 0. Years ago, you used to be able to get away with putting down 0 for these ones, but nowadays the exam boards won't let you do it. So you need to put down very small. You can get away with negligible. Okay? So, in terms of charge, we can have positive, we can have 0, we can have negative. So you need to make sure you're happy with that. Let me just get rid of that. Cool. In terms of location, then, we have nucleus, and we have in orbit, or sort of circling around the outside. Okay, so make sure you're happy with that. Make sure you've got it written down. It's one of those, you just have to know it. There's no easy way around it. I said there's not a great deal in science in terms of knowledge compared to some of the others, but these are sort of some of the fundamentals that you do have to make sure you've got written down. So, I said we'd come back and have a quick look at isotopes. Now, if you notice when we're looking at some of these, particularly chlorine and copper, I think they're the only two that you've actually got on this table, you'll notice that their mass number isn't directly, it's not a whole number. So chlorine, we're looking at 35.5. So we can have different isotopes. So let me just show you a couple of these. If we look at carbon, when we look at the periodic table, carbon is carbon 12. This means that in terms of protons, we're going to have 6. In terms of neutrons, we're going to have 12 take away 6, which is also 6. And we're going to have 6 electrons. Okay? So we need to make sure that actually happy with that. There is another isotope of carbon, and this is the radioactive one they use when they're sort of carbon dating. So about 1% of all of the carbon that makes up your body, and bearing in mind you're a carbon life form, the majority of the molecules inside our body are going to be carbon-based. And about 1% of that is going to be carbon-14, which is slightly radioactive. Now, it's not enough to cause us any damage, but it does mean that actually we can use it, that when we find objects or items or remains from thousands of years ago, by working out what the radiation levels are, we can actually work out how long ago it died, so when it was actually living. So in that case, we have carbon-14. So carbon-14, it still has to have 6 electrons. Tanishka, the mass number of an electron, it's about 1 over 2,500. From the exam board's point of view, just put down very small or negligible. Don't worry about it too much. Just don't put down 0. If you put down 0, it will be wrong. If we look at the number of neutrons for this one now, we've now got 14 take away 6, which is going to be 8. So you notice these two numbers here are different. Because this is only about 1%, it's not enough on this particular periodic table to make a massive change to the overall mass number. Okay, we'll come back and work that one out in a minute, but I'll show you what I mean. When we look at chlorine then, chlorine exists as 2 isotopes. About 75% is going to be chlorine 35. In fact, let me just move that 75%. Oh. To this side. So again, if we're working out our mass numbers, protons is going to be 17 for both, because it's chlorine, so it's got to have 17. Neutrons, in this case, we are looking at 18 there and 20 there. And electrons is going to be 17 because it's an atom, so it's got 0 charge on it. So that's our isotopes. But if we want to work out the mass number now, we can actually take into account this relative abundance. So to do this, what we do is we do a calculation for this would be 35, which is my mass number here, multiplied by 0.75 equals, and I would do 37 multiplied by 0.25 equals. So let me just bring up my calculator so I can do those while we're here. So it's 26.25. And if my calculations are correct, and we have 9.25. Add them together and you get 35.5, which is the mass given to you. Mass given to you in the periodic table. So we only generally have, we only sort of show chlorine and copper because actually there's a fairly large number of the isotopes. With most of the other elements, the number of the isotopes is so small, it doesn't make a big enough change to the mass number to warrant showing it to you on the periodic table. However, saying that, if you look at a lot of the periodic tables online, and I can give you a very quick, so I'm going to show you this. Let me just bring up one by the Royal Society of Chemistry. Which would be that one. Yeah. If I just add that window in. Okay, can you hear me now? Sorry, missed that completely. No idea what's going on. Can you just confirm now that you can hear me again? Brilliant. Thanks, Amy. Thanks, Tanishka. Okay, I'm not entirely sure where the sound dropped out then. So I'll just go through this. What I've done is I've dropped in an exam question. We've got they've given us the mass numbers and they've given us the percentages. I've converted the percentages into decimals. And then what I've done is I've multiplied each of the mass numbers by that fraction, by that decimal. Okay, thanks, Tanishka. I'll come back to the periodic site in a moment and see how that goes. And it's converted it into these mass numbers. Okay? By adding up... So yeah, I've multiplied the mass number by the depth fraction, worked out the proportion of the element that is that mass, added them together to get my average mass number. And that would be my relative atomic mass. Okay? Cool, that's annoying. I need to find out what's going on with that microphone if it's going to cut out like that. Okay. I'm not entirely sure how much you heard about the periodic table site. I'll just put it back up again. So in terms of this site, all I was saying is that if you look at the individual atomic numbers, as we're looking through, if you look just below this sort of number here, we've got the relative atomic mass, and that takes into account the isotope. And when you're looking at all of these, every single number has its own relative atomic mass, which means, they have their own isotopes. None of them are whole numbers. So pretty much all of them have an isotope, but most of them, the isotopes aren't in a large enough quantity, they're large enough proportion to affect the mass that you get given on your periodic table. So the only two they've put in is copper and chlorine. So they're the only two we really need to worry about in this case. Okay? Right. Okay. Let's have a look then. So, God, you'll love running live lessons with the technical glitches. Now, in fact, I'm going to put the periodic table up again because I want to be able to talk about it. We've said up till now that the electrons themselves are found in orbits or shells or energy levels around the outside of the atom. Now, when you go on and you look at when you go above GCSE, they will add a lot more information to what we cover at GCSE and to what I'm going to go through now. So we keep things fairly simple in terms of putting the electrons into electron shells. Now, if I put rules of electron configuration, things we need to worry about. We must fill each shell completely before moving on to the next one. And I'm going to give you some examples of this in a moment. Okay, so we've got that. Next thing we've got with this one then, the first shell can only hold 2 electrons. The second and the third shell okay, so from a GCSE point of view, that is all you're going to need to worry about at the moment. We may put 2 electrons into the 4th shell because we need to be able to do the electron configuration for the first 20 elements, but you will not be asked to go beyond that at GCSE level. Now, when you look at A-levels, you realise actually there are some other properties of these shells that we need to worry about. We'll start calling them different names. We'll start giving them, so they've got the s orbitals, the p orbitals, and the d orbitals. But at GCSE, we don't need to worry about that too much at the moment. It's something I can cover with people individually if you want me to when we're back in school. But for the moment, just learn how we fill them in. Now, if we start with basically the most simple one, so we've got hydrogen. I'm not going to draw all of the protons, neutrons, and electrons in on this one. I'm just going to worry about the electrons. So we've got hydrogen. Hydrogen has 1 proton. Okay, which means in an atom, it's going to have 1 electron. So that's nice and simple. I'm going to show my electron with a cross. You can do a circle, you can do E-. I don't mind at this stage, but I'm going to put a cross because it seems to follow on a lot more to later on. Let's look at the next one. Okay, so let's just move that up a little bit. There we go. So helium. Helium has 2 protons. So therefore, because it's an atom and has no charge, it will also have 2 electrons. So I can put 2 electrons in there. Now, when we look at the next one, which in this case is going to be lithium. Lithium has 3 protons. So therefore, it's going to have 3 electrons. So I'm going to put 2 electrons into my first shell, but it can't hold any more than that, and I've still got 1 electron left over. So in this case, I'm going to need another please let me move it. No. I'm going to put another shell in, and my 3rd electron's going to be there. Now we can show the electron configurations by writing like that. Okay? And you need to be able to do this for any of the first 20 elements. So I'm not going to draw all of these. It's well worth practicing going through and drawing them all out. I'm going to pick a couple. So I'm going to do magnesium next. So magnesium has 12 electrons because it's got 12 protons. So the configuration for this one, and we can do it in numbers before we draw them out if we want to, but I'm not. I'm just going to draw these out. So there we go. Now, 12 electrons, 2 in the first shell. If I've started off with 12, that leaves me with 10. So, okay, I'm going to put 8 into the next one because I know that my second shell can only hold 8. That leaves me with 2 more. Notice I've paired the electrons up. Couple of reasons. Again, if you go on to do chemistry later on, you'll find out actually they do pair up. So it's actually a better way of doing it. But also, if you spread them out nice and evenly around the outside, generally I find most students make counting mistakes when they're counting up the number of electrons in a shell when they spread them out around the outside, because it's very difficult to see at a glance exactly how many is in that shell. If you look at what I've got there at the moment, you can see straight away that second shell, it's fairly obvious there's 8 electrons in there. We can put the configuration down here. But actually, if I was to spread them out, I would actually physically have to count them. I couldn't just do it at a glance and work it out. Okay, so that's quite important from that point of view there. Another thing to note here, and I'm just going to do this and I'm going to stop for the day. I'm going to come back and do electronic config in a bit more detail next session. Is if you look at the last number, in fact, ignore the first 2 because they're not actually over a proper group. But if you look at the last number here, and to some extent with helium, okay, let me come back to helium. You'll notice it's the same as the group it's in. So lithium's got 1 as the last electron, so the outer electron, and that's the group. Magnesium has 2. It's in group 2. And you'll notice with all of these, once you actually work out the electron configuration, the group number tells us the number of electrons in the outer shell. I can go to the periodic table and I can choose any elements. I can pick iodine down here, which we don't even need to draw the electron configuration. And straight away, I know it's got 7 electrons in the outer shell because it's in group 7. The other thing we can work out is actually by working out the number of shells. So this one's got 1 shell, this one's got 1 shell, this has got 2, and this has got 3. That's equivalent to the period number. So we said before we got period 1, we got period 2, we got period 3. Notice hydrogen and helium, both in period 1, they only have 1 electron shell that's filled. If we look at group period 2, lithium's in period 2, it's only got 2 electron shells that are filled. Magnesium's in period 3, we've got 3 electron shells that are filled. If I was to take, I'm just going to take chlorine for a minute, and then I'm going to finish here for today. I'm not even going to draw chlorine out for a minute. I know that chlorine has 17 electrons. So I know that it's going to be in period 3, so it's going to have 3 shells. I know that it's in group 7, so my last shell is going to have 7, which means the other 2 must be filled if they're going to follow these rules. If I count them up now, 2 plus 8 is 10, plus 7 is 17, there's 17. So I haven't had to draw them out to work out what the electron configuration is. I just have to be good at using the periodic table. I'm going to finish at that point today, but what I will do is I'm going to start the next session with electronic configuration. And then we're going to carry on sort of going through, and we're going to start looking at the properties of groups 1, group 7, group 0, and we're going to talk about the transition elements. I will probably also then touch upon ions and how they're formed, because that's going to set us up for chemistry 2 when we look at bonding and structure, which is a much, much bigger topic. So enjoy the rest of the day, and I will see you in the future. And apologies for the technical hitch with the microphone.